present our work on projected sea level changes in the China Marginal Sea based on the dynamical downscaling. My supervisors are Xibing Zhang, John Church, and my domestic supervisor, Xianwen Bao. For decades, the global climate model continued to provide important scientific insight into the climate system estimation. However, the raw GCM output is not always appropriate to address the regional issues directly, because the coarse spatial resolution and biases relative to the observational data make it not adequate for the regional application. In addition, the GCM also require large computation resources. So on this background, the downscaling method is applied as one of the most useful tool to refine the GCM output. Generally, it can be categorized into the statistical downscaling and the dynamical downscaling. In this work, we employ the dynamical downscaling, which means the use of a high-resolution regional model to dynamically translate the effect of large-scale climate process to local scale. And the dynamical downscaling has been applied in many regions for the future projection. However, field works have been done in the China Marginal Sea. So here in this work, we focus on the sea level projection in the China Marginal Sea based on the ROMS. And the China Marginal Sea here includes the East China Marginal Sea in the red box and the South China Sea in the green box. And the broad and shallow continental shelf in the Marginal Sea here cannot be fully described in the GCM. So the ROMs here you can overcome the shortages of the GCM by applying higher resolution. And the sigma coordinate used in ROMs is more suitable for the coastal region simulation. And the second part for the model configuration, the spectral resolution of the region model is 1/12 degree, roughly 8 kilometers, and there are 30 layers in vertical. For the boundary condition, to exclude the sea level fluctuation caused by the net volume changes, the net water volume flux, namely the open boundary transport and the river runoff, is balanced at each time step to keep the regional mean sea level at 0. And the clamped condition is used for 2D volume flux and traces. And the radiation condition is used for the 3D momentum. To absorb the inconsistent energy on the boundary, the sponge layer within 2 degrees from the boundary is involved in, where the viscosity and diffusivity is increased from the interior to the boundary, and the nudging strength is increased from 200 days to 5 days. Because there is no sea ice model, the lowest temperature is set as minus 1.5 degree in the model. To perform the dynamical downscaling for the future climate change, it is necessary to establish a reliable regional model with a robust historical simulation. So for the historical experiments, the brand is used for the boundary condition, and the YiJin interim is used for the surface forcing through Bach formula. And the climatological monthly sea surface salinity from BRAM is used for the surface salinity relaxation. And the climatological monthly transport of the Yangtze River, which is the largest river in China, is also considered. The initial condition is based on a spin-up experiment in which the TS UV fields from the first day in 1994 of BRAM is forced by the YiJin and the BRAM of 1994 repeatedly. When the model is quasi-stable, the first day state of the 6th year is used as the initial condition. For this part, we did a lot of model validation of the sea level, temperature, and ocean current, which indicates that the regional model can reproduce the historical ocean state reasonably well. And then we are confident to move to the future. Because of the time limitation, I want to show the validation results here. So for the dynamical downscaling, is carried out as the following step. First, the climate change signal delta F, which includes the mean and the seasonal signal, is obtained from the differences between XIS 1.0 future monthly climatology and XIS 1.0 historical monthly climatology. Then this data F is added to the historical experiment forcing, and then we can get the future experiment forcing. And the result forced by the future experiment forcing is get from the written model, and finally the downscaled result is obtained from the differences between the future experiments and the historical experiments. Specifically, the climate, as shown in this table here, the climate change signal data F of the ocean variable is called data FO, and the climate change signal of the atmosphere variable is called data FA. Including the XIS 1.0, totally 8 semi-5 models are downscaled, which all perform pretty well in the sea level simulation, and it is the semi-5 ensemble in this work. And by repeating these 4 steps 8 times, we can get the downscaling ensemble. Before I show the results, I also want to introduce another experiment we did, which is called ensemble force experiments. So in these experiments, the data FO bar and the data FA bar is applied for the boundary condition and the surface forcing respectively. And the bar here means the ensemble mean of these 8 selected GCMs. Here is the result. It is the differences between the future and the historical period. A is the mean sea level change, and B, C are the summer and winter SST change respectively. And these 3 figures come from semi-5 ensemble. And here is the result of the downscaling ensemble, which is very similar with the semi-5 ensemble, but with more details revealed in the marginal C. For example, here is reflect crucial intrusion change, and here is the sea surface circulation change in the South China Sea. And here is the ensemble force the experiment's result. If you compare it with the downscaling ensemble, you can find that they are almost identical, which means the different components of the climate change signal from different GCM are almost linear. And it is very important for improving the efficiency of the downscaling, which means if we just care about the ensemble mean from the downscaling results of the different GCM from multimodal, only one downscaling experiments forced by the ensemble forcing is needed rather than repeating many times. And to further investigate the mean sea level change in the marginal sea, we did 2 perturbation experiments. So in the number 2 and the number 3 experiments, the climate change signal is applied for both boundary condition and surface forcing. And here, in the boundary only experiments, the climate change signal is only applied for the boundary condition while keep the surface forcing unchanged. Similarly, for the atmosphere only experiments, the climate change signal is only applied for the surface forcing and the boundary condition is unchanged. So based on these 2 perturbation experiments, the contribution comes from the ocean for this atmosphere can be separated. And here is the result of these 2 perturbation experiments. So the figure A4 is close to the figure A3, which means the boundary condition change can explain most of the changes in the mean sea level, while the boundary condition change contributes less to the sea surface temperature and only limited near the boundary. Compared with the boundary condition change, the surface forcing change contributes less to the mean sea level change, but can explain most of the changes in the SST. Furthermore, if we get the sum of these 2 perturbation experiments, we can get these 3 figures, which is close to the ensemble force experiments, which means the climate change signal components from ocean and atmosphere are also linear. And also it proves that our decomposition is successful. So here is the basic storyline of what we did for the mean sea level change. And in the end, I also want to briefly introduce what the ongoing work about the extreme sea level. Compared with the mean state change, people may be more interested in the extreme event. And in this work, the generalized extreme value distribution is used to describe the extreme sea level change. The idea is that the climate change signal can be separated into the mean part change, the seasonal part change, and the non-seasonal part change. And further, this non-seasonal part change can be separated into the low frequency signal change and the high frequency signal change. So in this work, we want to discuss the extreme sea level changes caused by these three different components respectively. Thank you.
Thanks, Yi.